Okay, now we are ready to complete the second half of Lecture 26. Here we're going to be introducing the interaction representation. The interaction representation is halfway in between the Schrodinger and Heisenberg representation. We essentially use a Heisenberg representation for the H0 and a Schrodinger representation for the V of t. If that sounds confusing to you now, don't be concerned. It should be confusing to you. We really have to go through these steps and see precisely how all of this is going to work. So, as I had mentioned before, we start with a Hamiltonian h of t that can be separated into two terms. One of them is the time-independent term that we call h0, and the other is the time-dependent term that we call v of t. That term is expected to be small, but again, I want to remind you that small does not necessarily mean the magnitude or norm of that operator is small, just that its total effect on the system is small, so that I can have a very large perturbation applied for a short period of time, and that might still qualify as a small perturbation. Okay, we're going to be working with the eigenstates of the time-independent Hamiltonian H0. These eigenstates, of course, are independent of time. They're stationary states. They satisfy H0 acting on n is equal to E0n acting on n. And we're going to define the psi interaction of t to be the Schrodinger wave function multiplied by e to the plus I over h bar h0 times t minus t0. Notice that the t minus t0 is not the argument of the h0. It is simply a time factor that is multiplying t minus t0. Now, bear in mind here that this exponent has the opposite sign to what one would have for the time evolution operator. You can think of this as that operator is canceling the time evolution in the Schrodinger wave function corresponding to the evolution with respect to the Hamiltonian H0. And then just like we did with the Schrodinger and the Heisenberg representations, we're going to define an a sub I of t, an interaction representation operator, as e to the I over h bar h0 times t minus t0, a Schrodinger of t e to the minus I over h bar h0 times t minus t0. And we're going to use that for the potential to describe an interaction picture version of the potential, which takes the form vi of t equals I over h bar h0 times t minus t0 v Schrodinger of t e to the minus I over h bar h0 t minus t0. So what you can note is that the interaction representation of h0 will equal the interaction representation of h0 Schrodinger of t, which is just h0 of t, which is just h0 because h0 does not have any time dependence. And that all follows from the fact that h0 commutes with any function of h0. So in particular, commutes with e to the I over h bar h0 times t minus t0. Okay, we are now ready to talk about the Schrodinger equation. So we're going to look at the Schrodinger equation for this interaction representation wave function. I just look at I h bar d by dt acting on that wave function. It is simply defined in terms of the Schrodinger wave function. So we're going to get two terms. The derivative will act on the exponential, and the derivative will act on the state. When the derivative acts on the exponential, we are going to get a minus h0. And when the derivative acts on the state, I'm going to get an h Schrodinger of t. Now, because the h0 commutes with e to the I over h bar h0 times t minus t0, I can bring that to the right-hand side. It has a minus sign in front of it, and it's going to cancel the h0 that I get from h Schrodinger of t, which, let me remind you, was h0 plus v Schrodinger of t. So we're just left with the v Schrodinger of t, and now if I introduce a factor of 1 equal to e to the minus I h bar h0 times t minus t0 times e to the I over h bar h0 t minus t0, in between the v Schrodinger and the Schrodinger ket, you find that we now have this as v interaction picture of t acting on psi interaction picture of t. So notice we've gotten this very interesting Schrodinger equation. I h bar d by dt psi I of t is equal to vi of t acting on psi I of t. In many respects, it's looking like we have a time-dependent problem where the time-dependent Hamiltonian is just the potential or the perturbation written in the interaction picture. Okay, we know how to solve those kinds of time-dependent problems. It will involve a time evolution operator that we call the interaction representation time evolution operator that carries the interaction picture wave function at time 0 to the interaction wave function at time t, just like we were doing before, and it's going to satisfy this equation of motion, IH bar d by dt of u interaction of tt0 is equal to vi of t u interaction of tt0. This is exactly the same equation as we solved before, although in the last time we were calling it h of t. But that's just the name for an operator. So we immediately know what the solution of this equation is. It's this time-ordered product with respect to the interaction picture potential. And so we can write that as the time-ordered exponential e to the minus I over h bar integral from t0 to t, the interaction picture of t prime dt prime. And of course, as you remember, what that means is we're really writing that as the summation that's written below. The power series looks like an exponential with a minus I over h bar to the n and 1 over n factorial, but then we multiply by this nested integral that goes from t0 to t. It's an n-fold nested integral, and it involves the time-ordered product of all of these v interaction potentials of the different time arguments. This expansion has a name. It's called the Dyson expansion for the evolution operator. And we want to note in particular that because psi interaction of t is e to the I over h bar h0 of t minus t0, I can get back psi Schrodinger of t by looking at the following expansion. We know psi Schrodinger of t is u Schrodinger of tt0 times psi Schrodinger of t0. But we also know that that whole thing is equal to u interaction of tt0 times psi interaction of tt0. And so if I rewrite psi interaction of tt0 in terms of e to the I h bar h0 t minus t0 psi Schrodinger of t, and I recognize that at t0 these states are exactly the same. Psi interaction of t0, psi Schrodinger of t0, and psi Heisenberg of t0, they're all the same because u of t0 is equal to 1. And from that I can now derive an operator identity by equating the operator u interaction of tt0 with e to the I over h bar h0 t minus t0 u Schrodinger of tt0. If I multiply both sides by e to the minus I over h bar h0 t minus t0 on the left, we'll get this nice boxed equation. U Schrodinger of tt0 is equal to e to the minus I over h bar h0 of t minus t0, time-ordered product e to the minus I over h0 integral t0 to t dt prime v interaction of t prime. This is the expansion that we wanted to find of the evolution operator, which is u Schrodinger of tt0, in a power series in the perturbation v. It will be used to determine an expansion for time-dependent perturbation theory in just a couple of lectures. Notice that this is something you probably would not have guessed. We had something that initially had a time evolution operator of h of t in the time-ordered exponential, and we somehow managed to factor out an e to the minus I over h bar h0 times t minus t0 and converted the h of t into vi of t. That's kind of remarkable if you think about it. Now we're going to have another way of showing this derivation by looking at the equation of motion. And it's going to bring about that factorization idea in more detail. Okay, so remember, for any operator that I put into a time-ordered exponential, IH bar d by dt of the time-ordered exponential of minus I over h bar integral from t0 to t dt prime a of t prime is equal to a of t times the time-ordered exponential e to the minus I over h bar integral from t0 to t dt prime a of t prime. So let's put that in for our Schrodinger representation of the time-ordered exponential, but we're going to rewrite that Schrodinger operator in terms of this interaction picture. So the Schrodinger operator is e to the minus I over h bar h0 t minus t0 time-ordered exponential of the interaction picture potential. We now take the derivatives with respect to time. We have two terms. First, when the derivative acts on the e to the minus I over h bar h0 t minus t0 term, you see there's a t that is in the exponent, and when I take that derivative, I'm going to pull down an h0. and then I'm going to have a derivative acting on the time-ordered exponential, but I can actually calculate that derivative from the equation of motion. It will pull down a vi of t. Now I can take that h0 and pull it out to the left, and I can recall vi of t is written as e to the plus I over h bar h0 t minus t0, v of t e to the minus I over h bar h0 t minus t0. So I can write e to the minus I over h bar h0 t minus t0 vi of t equals v Schrodinger of t times e to the minus I over h bar h0 t minus t0. If you do not see this identity, please carefully look at the definition of vi of t, pause this video, and make sure you see that that identity holds. What we've done is we've just multiplied both sides by e to the minus I over h bar h0 t minus t0. Now notice you can think of this identity in a different way. You can think of this identity as a operator reordering identity. E to the minus I over h bar h0 t minus t0 v interaction of t. If I move the exponential factor through the v interaction of t to the right, it becomes v Schrodinger of t times e to the minus I over h bar h0 t minus t0. That's kind of a neat way of thinking about exactly how this equation is structured. Okay, now that we're clear exactly how that works, we're going to use that to move the vi of t, or move the v to the left. So you see here in this equation of motion, when I took the derivative, I have an e to the minus I over h bar h0 t minus t0 vi of t appearing after I took the derivative. I'm going to replace that by v Schrodinger of t times e to the minus I over h bar h0 t minus t0. And you see I now have pulled all the way out to the left h0 plus v Schrodinger of t multiplied by u Schrodinger of t t0, because the expression on the right is e to the minus I over h bar h0 t minus t0, time-ordered product of the interaction potential. So what we have shown is I h bar d by dt of this operator, which we know is the Schrodinger time evolution operator, is indeed equal to h of t times this operator. And the operator, when I evaluate it at t0, it's just equal to 1. That tells us this operator is the Schrodinger time evolution operator. And we've proved the result directly simply by using the equation of motion. Okay, that is all that we have for this lecture. We'll see you again in the next lecture. Be safe.